Okay, I'm gonna go over Project 5 of NAND2Tetris. I'm in an airport, so it's a little noisy, and I think I have a cold. So the sound's not gonna be great on this, but I'm gonna go over how I did this a little bit, what I went through, some of my thoughts on it. So in this project, it's Project 5. You have to build memory for the computer, the hat computer, and then you build the CPU of the hat computer using the ALU and some other chips, and then you put it all together and make the computer itself. So I have the code here for the memory, the CPU, and the whole computer. Alright, so I'm going to start off talking about the memory. So the memory is 24 blocks. 24 kilobytes of addressable memory. So you only need 15 bits for an address. The low 16 is going to be just a regular RAM, and then the 8K on top of that is going to be the screen, and the very last bit is going to be the keyboard. So the resources I used are on the NAND2Tetris website here. You can go to Projects over on this tab, and then I click on these like PowerPoints, but they also have sections from their book that have helpful information. So all these tabs I'm going to flip through came from this. So there's the CPU diagram that they recommend using. This is the memory map. So as you can see, it's just a regular RAM chip, 16K, and then you got the screen here, which is 8K, and then the keyboard. That's the address of the keyboard. That'll come in pretty handy.
It's going to be a completely full flight this evening. Every seat is going to be accounted for. We are looking for 14 volunteers who are willing to help us out, checking those carry-on size bags free of charge this evening.
You need to decide which block of memory you're going to access. I used a demuxer, and for the bit to choose which block, whether it's going to be 16K or the higher screen memory, I used the highest bit of the address as the load bit. So obviously, if it's a 0, it's going to be lower memory location, so it's going to be the 16K. If it's higher than that, which is the screen memory, that last bit is going to be a 1. That most significant highest bit is going to be a 1. So that will choose which way the load bit is going to go. Anyway, that's how I did this part. So the screen is the high RAM, and then I used a muxer on the memory out to in the same way. Basically, I used the highest bit as a load bit, and then for the keyboard to decide if the keyboard would be outputting or not. So let's see how I did this. So the memory, the output of the memory is decided first by that load bit to decide if it's the high screen memory or the low RAM 16K that's being outputted. And then you have to decide, well, is the keyboard going to be outputted? Well, I took my final output and I ran it through a demuxer, and for the select bit on the demuxer, I basically took the binary version of the keyboard address, which is let's see, it's a 15-bit address, so it's all the low bits are zeros except so it's all zeros except for the highest two bits. Those are 1s. So what I did was I used NOT gates to make all the lower bits to make inverted versions of them. And then I used AND gates, ANDed all those inverted versions plus the 2 that are supposed to be 1s, and then that gives me a final bit that will only be a 1 if the exact address of the keyboard is entered as an address. If that's the case, then it will select the demuxer will select the keyboard as an output. So yeah, that's how I did the memory part. That was the trickiest part, is figuring out exactly how to get, like, if the keyboard address was entered from the CPU, like how would I get the keyboard out? And that's how I did it. There may be an easier way, I'm not sure, but that was my method. Alright, the CPU, it was like super daunting. I mean, it looks simple right here in this little thing, but then it's got the ALU, the program counter, it's got A register, D register, you got the NG, the flags that come out of it, the 0 flag and the whatever the other flag is. Yeah, so that's the ALU by itself. And then this is the internal thing. So I just did it one pin at a time. I started like throwing this muxer, the A register, the D register, the ALU. I just started adding these into my programming and then just connecting the pins one by one. The pins that are here that are obvious, just connect those. And then the ALU control bits, those are actually easier than you would think. So they go in right here at the top of the ALU, all these different control bits. And then if you look at the instruction, you got these C bits here, the compute bits in the middle. Those determine what the CPU does. So if you just drop those in right into the top of the ALU pins, input pins, that will make the ALU work correctly. So you route those pins from the instruction input into the ALU. The destination will let you know if it's going to the so here, like, obviously you can use these and a few gates to determine if the output of the ALU is going to the A register, the M register, the D register, whatever. And then jump, that was the most complicated part. So here's my code. A register, D register, pretty self-explanatory. Mux, those are the two muxers that were on that map, the CPU diagram. What is it? Yeah, so I just named these Mux 1 and Mux 2. The ALU, I already talked about that. And then, okay, so the jump thing, so this part I just renamed them to make it easier. The jump bits. The jump bits come from the J section of the instruction. So you combine those. This section is super helpful. Combine the jumps, and then this part right here, if something's greater than 0 or less than 0, you can use the ALU. Where is it? These two outputs from the ALU, combine those with the jump bits, and you can basically make a truth table. So I made all these conditions, whether to jump or not, and then the jump, yeah, so this is all how the jump stuff here. Creating those conditions for the jump bit. Then, if the jump is true, if you're going to jump based on those conditions, then you will set that as a load to the program counter. That means the program counter is now going to accept an input rather than just incrementing. If there is no jump, the program counter is just going to increment by 1. So that was kind of a hang-up for me because the program counter here has 3 inputs, and then the program counter on the CPU thing, it's got only 2 in the top there. So that threw me. So just, yeah, the program counter will it will increment unless there's a jump. Then if it jumps, it will then take whatever is in the A register, and that will become the new address that it's pointing to. Okay, so yeah, this is basically just about figuring out where all the control bits go. And I'm hoping I'm scrolling this slowly enough so that anyone who wants to use it can see, including my future self. So you can pause the video if you need to. My little comments, hopefully they're enough. Okay, now the computer. I thought this was going to be harder, but it's actually super easy. The trippiest part is like the reset bit, the in. That's the only thing. There's no output, and that's because once you build the computer, it's an enclosed system. You got the input is basically the on switch. So you turn the computer on. It resets everything. It resets the program counter to 0, and then the program counter automatically points at the ROM address. So the ROM is whatever we put in the hack assembly. I compare it to writing a program and then having it on a cartridge, and you plug it into like a Sega Genesis or one of those old computers that took cartridges, and you turn it on, the program counter automatically starts reading from that cartridge. The cartridge is already pre-assembled, the program's already written, and then if the program from there indicates that the RAM should be accessed, then it will start pointing that direction. So all you really do is these simple connections between the ROM, 32K ROM, and then the CPU, and then the RAM. So yeah, not much to say there. That was like super easy. The memory, the trickiest part was just figuring out how to read the keyboard input, or yeah, getting the keyboard to work right, and then the CPU. Figuring out how to handle jumps. And when you're jumping, in essence, all you're doing is changing the contents of the program counter, so it points to a new
You're headed
address.
to Las Vegas. We are still looking for any volunteers who are willing to help us out. Check in those carry-on size bags free of charge. We are looking for 9 more.
The worst part was just getting started, honestly. And to get started, I just started connecting pins. Once I got everything connected that's here, then I started looking at the program, the control pins, and I thought, what would need to change for the A register to change? That's a control for that. and the control bits for the A register, the load bit for the A register, the D, those are basically just the destination. So I think I didn't cover that. Excuse me. The destination bits are in the instruction. These 3 Ds right here. Here's your truth table. If they're all lined up like this, then the DM are going to be the destination. So you're going to load D, and then M is just the output. So that'll be right to memory. And then the jump bits, I already went over that in pretty good detail. So it felt pretty good to get everything together, get it all working. Oh, one more thing I wanted to touch on. Once you get a basic framework for this and you connect all the control bits like the way you think they're supposed to be, let me jump back real quick. So this bit right here, the most significant one on the instruction, if that's a 0, you don't need to worry about all the rest of this crap. So your first muxer is just going to be that, like whether it's an A instruction or C instruction. If it's C, then all this stuff is going to come into play. If it's A, then all these V bits are just address, or they're going into the A register. Okay, now what I was going to say is, once you get all this together and you think you got the program running, you're just going to run it in IDE. Yeah, so you're just gonna go to Project 5. Okay. So you're gonna load it up in here, you're gonna run it, and then look at your output. If it doesn't seem right, if something doesn't seem right, you just go through it step by step here. It's not gonna do it because I don't have my code in here, but step by step, and when you look at the compare file, if something's wrong, it's going to turn red, and you can look exactly all the address bits and like all your pins, see where everything's at, and like see where things didn't go. You just trace the pathway of the pins, trace the instructions, and this is like, I guess, the debugging part of it. That was kind of annoying, but it was also kind of a fun challenge to go through like line by line, fix my errors, rerun everything, watch it go a little further, and then fix that error, and then it goes a little further every time. Pretty soon the whole thing's working like it's supposed to. So don't get discouraged, just one thing at a time. You don't have to do this all at once. You can't do this all at once. Anyway, that is NAND2Tetris Project 5. I hope this is helpful to someone. If not, then it'll be possibly helpful for me in the future.